And this is how the warp drive works. Hi, and welcome to the First Interstellar Institute. Today we are going to talk about Warp Factory, a powerful tool for numerical analysis of various space-time metrics, including warp drive metrics. But before we start, let's remind ourselves about warp drive concept. Warp drive was proposed by Miguel Alcubierre in 1994, and the idea is rather simple. Look at this cartoon. We have 2 points, A and B, and space-time between them. And we know that space-time can bend. For example, mass bend space-time. And so what we need to do is to keep the space around our ship the same and expand the space behind the ship and contract the space in front of the ship. And so, as you can see, doing so, we've made most of our way to our destination without moving hardly at all. And this is how the warp drive works. We expand space behind the ship and contract space in front of the ship, leaving the stable bubble around our ship. And so the space in this bubble hasn't been warped, as you can see on this cartoon. And what is cool about this idea is that we can travel faster than the speed of light. You see, inside this bubble, we hardly moved at all, and the speed of light is the barrier for the speed in space-time. So you cannot travel faster than the speed of light in space-time, but space-time itself can move faster than the speed of light. And we know that in the early stage of the universe there was a period called inflation, where the universe expanded with the speed faster than the speed of light. And we know this fact experimentally. Here on the left you can see another cartoon of expansion and contraction of space-time, and this all is just wibbly-wobbly, timey-wimey stuff, and let's just look at math. Here on the left you can see the Alcubierre metric in Cartesian coordinates, where f is the shape function and r is the radius of the warp bubble, and this is a time-dependent metric. So this metric moves, and you can see it contains Vs, which is the speed of the bubble. And for example, if I substitute the speed equal to 0, this metric will be transformed to the simple flat Minkowski spacetime. Then, given our metric, we need to go and solve Einstein field equations, and we want to find out the stress energy tensor, which will tell us what is the matter and its distribution that is needed to create such a geometry. And if you want to know more about this, I encourage you to watch previous video about wormholes, where we dive deep into the mathematics behind Einstein field equations. But thanks to Miguel Alcubierre, who done all of these computations for us, we can just look at his results. And here is the 0,0 component of our stress energy tensor, which is responsible for energy density, mass energy density. And as you can see, it contains the minus sign, which means that we need matter with negative energy density, and we can also say that this matter is exotic. For example, if I have an apple made from exotic matter, it will repel, for example, Earth. It will try to fly away, and this is rather strange. I also have this plot which shows the distribution of this exotic matter around our warp bubble, and this picture was made using this warp factory, and so we will talk about this later. But what you can see from this picture is that not just exotic matter is required, but a lot of exotic matter is required to create this warp bubble. And some estimations tell us in optimal case that we need the mass around the mass of Jupiter, or this exotic mass, to create this geometry. I also need to stress out that our ship in this case moves in X direction from left to right, and also that our ship is located here in the middle, so this matter is around our ship in this bubble. And there is also a question like, should this exotic matter move faster than the speed of light to create faster than light travel? Because as we know, in GR, in general relativity, mass bends space-time. And so if you want to bend your space-time in this fancy way as in warp drive, you also need matter. But if you move faster than the speed of light, should this matter also move faster than the speed of light? So this is questionable. And then after Alcubierre's proposal for warp drive, other people were trying to optimize the energy requirements for warp drive. They also wanted to eliminate this need for exotic matter, because, you know, in universe there is no exotic matter as we know it for now. We know that universe expands, but we cannot find exotic matter that easily, you know, and especially in quantities such as the mass of Jupiter or more. Other notable proposals were made, and first let's look at Chris van den Broek bubble compression model in 1999, and he was able to reduce the exotic matter requirements. So then Atario vorticity-based warp drive 2002, and in this work he provided an alternative mechanism for warp motion without requiring space-time expansion, but as you can see, it still required exotic matter. Then in 2021, Eric Lenz, and in his proposal he was able to create a warp drive geometry that doesn't require this negative energy. And this is the speculative work because as far as I know, the team from Warp Factory proved that this geometry also requires this exotic matter. Let's take a look on this paper analyzing warp drive spacetime with Warp Factory, and specifically onto the example of Lenz metric. And here you can see this is the energy distribution. This is inversed 0, 0 component of stress energy tensor, and as you can see, it also requires this exotic matter in huge quantities. And so, as we saw before, people were trying to come up with different metrics that reduce these negative energy requirements, and this is rather hard if you're doing this analytically by hands, for example. And a much better idea is to create a numerical solver that is able to optimize your metric and automatically find out the best metric with this minimum exotic matter requirements. And this is all about warp factory, and this is what we're going to talk about right now. But before we're going to do this, let me show this cool animation. This is the warp bubble around the ship, and I guess on this video they were not trying to show the distribution of matter, so it's transparent, and this is really cool. So you can see how the background image is distorted due to the presence of this warp bubble. This is gravitational lensing effect. It's really cool, you know. And also this video where this Alcubierre drive passing in front of Earth, you can see this distortion. You know, some people claim that this UFO objects, they will definitely use this warp drive technology, and this tic-tac objects sort of look like a bubble, but this all is rubbish, because if it would be so, then we would see this huge gravitational lensing effects, as you can see on this video. And so let's take a look on the warp factory. So you have to go to applied-physics.gitbook.io/warp factory, and so here we are on this website. And what is the warp factory? So warp factory is a set of functions written in MATLAB, which is designed to model warp spacetimes using Einstein's theory of general relativity. Its development is focused on providing a numerical framework to analyze the physicality of spacetime, which is a unique focus in the development of warp solutions. And so what warp factory can do? It can find the stress energy tensor using a numerical solver. It can analyze for null, weak, dominant and strong energy conditions. It can do really nice plotings and so on. It also can use GPU for intense computations, and this is a development team, and shout out to this development team. You guys are amazing. This is a really nice tool. Let's now install warp factory. To install warp factory, we first need to install Git, and you can go through this link and install it on your device. And then you have to have MATLAB. So I do have MATLAB, and I also have the Git installed. So next we need to clone warp factory from GitHub, and for this you have to go through this link, press code, copy this link, go to your MATLAB. So right now it's launching, and come on, so we have to press new project from Git. We have to paste our link right here and retrieve yes. We need to name the project warp factory, done. Creating a project. Nice. Really nice. Then we need to add all folders and subfolders to the MATLAB path. So we need to go home, set path, and add with subfolders, clone project folder, and click OK. So where we are? No. So this is the project folder. OK. So right now it picked all of these folders, and we need to save it. And then we have to press close. OK. So let's take a look. So here we are. And what do we have? We have different folders. We have examples. Let's take a look. It's called my first metric. Here's the command window. And the structure in MATLAB is the same as on the website. So let's take a look on the website. First thing is the spacetime. So as you can see, the goal of Warp Factory is to construct spacetime and evaluate them for physicality and then visualize their structure. So first we need to set up spacetime, then compute stress energy tensor and do our analysis and also plot results. And let's take a look on the examples. So here is the process of constructing our first metric, and let's just look at default metrics. So it's the same. Default metrics in Warp Factory include Minkowski metric, Schwarzschild metric, Alcubierre time-dependent, Van den Broek, Lenz, Alcubierre K-moving, Van den Broek K-moving, and Lenz K-moving. So a lot of standard warp drive metrics. They are already built in Warp Factory. We just need to initialize them correctly. For that, we need to specify these parameters that goes into these metric functions. For example, for Schwarzschild metric, we need to specify grid size, world center, RS. RS is the Schwarzschild radius, and as you can see, so it's hard to miss this parameter. Grid size, it has 4 values because we are in 4 dimensions. The first value is for time components. We are analyzing static metrics, so we need only one time component, only one slice. Then these values are for 3 space components, x, y, and z. And as you can see, we divide our space into discrete points, and for example, for x direction we have 20 discrete points, and changing grid size will greatly affect our computational time, because more points you have, longer you will do your analysis. And so let's just try to put this into MATLAB. In command window, I copied all of this script, I paste it right here, I click enter. Right now it does computations. You see it initialized my metric RS. I see right here my parameters, and So these are the components of my metric that has been plotted, and here they are. And well, it's hard to make a reason from this. Let's continue our exploration. So, and also we can plot, for example, Alcubierre metric. It can be time dependent, and in this case we need to take, for example, 5 time slices, or it can be comoving. So these warp metrics do not move through space, so hence the name comoving. So we modify Alcubierre metric for static case, and in this example we have only one time slice. And so let's again copy this and paste, and here they are. These are the components of our metric tensor plotted in our space-time. So only space, because time is only one component. And you can do this for all of these metrics, and it's all pretty cool. Then this section describes how we can build our own metrics, which is what Factory all about. So you have to be able to make your own metric and compute stress energy tensor and analyze your metrics and so on. But we will do this a little bit later. Let's for now work with default metrics. So, and the next section is energy tensor. This is what we want to know, from our metrics. And to compute energy tensor, it's quite easy. We again specify these parameters that are going into our metric, and we define our metric, and we compute energy tensor just by calling this function get energy tensor, and we input our metric. So pretty simple. I'll do this in my MATLAB, and I have my energy tensor like this. So then I can do basic plotings. So I made a mistake. I do this. And as you can see, here are the different components of my stress energy tensor. This is 0, 0 components, which is responsible for mass energy density. And as you can see, for example, here, this actually the picture which I showed you before. This is the distribution of matter and energy that is needed to create our warp drive. And as you can see, these are negative values. It's minus 1.5 times 10 into the power of 40, so quite a lot. And this is not kilos, it's joules, joules per meter cube. So I hope I spelled it right. So yes, it is. And for example, we can again go to this definition of metric, and for example, you see when I'm specifying Alcubierre metric, I input the speed, as you might remember from our introduction to warp drive physics. So I can input velocity equal to 10, and right now this is about 10 times the speed of light. And let's see what we will get from it. Again, I compute energy tensor and I do my plotting. And what should I expect? And as you can see, I again have this exotic matter, negative energy density, but right now I have 10 into the power of 42, so I need 2 orders of magnitude more exotic matter than in the case of slower the speed of light, speed of my warp bubble. I can also increase the grid size of my metric. I will just replay this by 50. That's it. And again I compute energy tensor, and right now it will take more time to run, and so it's done. I'm deploting. So the values are the same, but you see the quality of image is rather different and much nicer. So these are all like components. There are how much? 16, yes, 4, 8, 12, yes, 16 components of my stress energy tensor. But I know that 0 component is responsible for energy density, mass energy density, so that's why I'm looking at this picture and I can reason something from that. For other components it's hard to make a reason. What else can we do? There are a few more things. It's a different method of computation. Then there is the GPU computation, and I do not have a GPU, so I can't do any of this. And there is a section of analysis. You can analyze your energy condition, which is null, weak, strong, and dominant. And from there also you can say how much exotic is your matter. And you can try this on your devices. I do not have a GPU, so sorry. And there are other cool things such as momentum flow. Let's just plot it for fun. What is this? Again, I do energy tensor computation and I get momentum flow lines. So okay, so I need to, okay, this is how it looks like. So I guess this is again about energy distribution. So it looks like our 0 component of stress energy tensor. So finally, let's create our own metric, because that's what it is all about. We have to create our own metrics, analyze them, and hopefully find out warp drive without exotic matter or something like this. And for that we need to do the following thing. We have to go inside metric folder and create new function. So metric folder is right over here. Metric folder contains all of these default metrics. So I click right and what should I do? New, and then I have to specify function. So now I have my function and I will call it wormhole, because I want to analyze the wormhole space-time metric. So that's it. Let's, as an example, take a Schwarzschild metric, which is located in our metric folder. I will just copy all of that, paste it right here. So you see, you need to replace the function definition and define needed parameters. For example, for Schwarzschild metric, the parameters are the Schwarzschild radius metric params are S, and that's it. For the wormhole, we will have our own custom parameters. And then I need to fulfill this definition of the metric. You see, they ask for equations as a function of t, x, y, and z, because as far as I know, warp factory only works with Cartesian coordinates, and it doesn't work with, for example, spherical coordinates, which is kind of sad. And we have to specify here our functions of our metric. So components by components, like for example here in Schwarzschild metric, every component has its own value, which comes actually from metric in Cartesian plane. And for example, we can look at this. So Schwarzschild, not here, so here, metric module, metric library, and for example Schwarzschild metric, and you see Schwarzschild metric in Cartesian plane has the following form. It's more difficult than in spherical coordinates, and all of these values are in this code. So for example, this is 00TT GTT component. It comes from here. So this is it, and actually there is a mistake. You see, it's not squared, it's without power actually. So guys, there is a mistake. Then dx squared again. You see this. So this is. So these are diagonal elements, and these are cross elements. So this is xx metric tensor component, and yy and zz, and so on. And so xx, yy, zz, and then cross components, we write them over here. And so right now we have to write in the same form our wormhole metric, and so let's do this. But first we need to rearrange our metric from spherical coordinates into the Cartesian coordinates, and we can apply the following equations to our metric, and from there find out the metric in Cartesian coordinates. And to do this transformation, I'm using Wolfram Mathematica, and here is my wormhole Morris-Thorne metric. Here is my shape and redshift functions, and if you're not familiar with that, I encourage you to go to our previous video where we talk about wormholes, and it's really cool. And here I define r, theta, and phi. I also do derivatives of these angles and the phi, dr, and I just substitute this into my metric. And because they are right now written using Cartesian coordinates, I can do this transformation, and here it is. Then for convenience, I replace these values with a, which is just a radius, and so on. And then I rearrange my metric into this form where I can pick components for example, dt and d. So this is gtt, gyy. These are diagonal components of my metric tensor. This one, and these are the. This also is one of the diagonal components, and these are the cross components. And right now I need to substitute them into my MATLAB code. And so this is my wormhole metric. You see, I changed the name of this function. Now it's called wormhole. It takes grid size, world sensor, and R0, and R0 is the wormhole throat radius, which is the minimum radius of the wormhole. And then I specify parameters, metric parameters R0, Everything else is the same as in Schwarzschild example. And so then I just replace, for example, GTT 00 component of my metric with values from Wolfram Mathematica. I also specify that the speed of light is equal to 1 because in Schwarzschild metric they also use a unity for speed of light. And so what are the differences between these two examples? You can see. Well, it's clear that I just insert my new values into these components and so on. And let's see if it works. So let's call this function, and first I need to again specify grid size. I specify the world center, and what else do I need to do? I need to specify R0 equal 1, and now I can call my metric function, and I write metric equal to, and so wormhole and all of that just goes in, and I successfully created my metric. And next let's compute energy tensor. Okay, it's also working. Now I can plot my metric first. Let's do this. So these are the components of my metric plotted, and I can also plot the energy tensor. And I should expect exotic matter because wormholes require exotic matter for the existence. And this is 00 component, which is responsible for mass energy density. And as you can see, there are minus values, so I guess this is what it means. And I'm not sure about this, how it deals with wormholes actually, because you see there is different topology for wormholes, so there is a hole in it. And well, but it shows some negative mass energy density, and it's okay. So values are again 10 into the power of 42, and it needs more exploration. But as a basic example, you can now, for example, construct your own metrics, or you can modify existing metrics and see what will happen to the energy requirements. And maybe you will be able to reduce the requirements of exotic matter just by a little bit changing the Alcubierre, for example, metric. And you can find it right here. You can find these metrics. So for example, this is Alcubierre metric, and this is Kamovin metric with only one time component for initialization. And here you can see again components, and this is shape function. It's more clear for Schwarzschild example. So you can play with this maybe components and see what will happen. Okay. And also I want to stress that in this example I haven't shown the energy condition calculations, but you can find them right here and in the section of analysis. And this calculation requires GPU. I don't have it, but you can at least watch what's going on, and this is how it looks. This is the computation of energy condition for all space where you work, not just, for example, single point. And here they compute energy condition for Alcubierre metric, and it's all negative. Okay, so it's now weak, strong, and dominant, all of them in a single line of code, sort of. You can just call these functions, and get your results just from the metric, and this is really cool. And so right now I wanted to show you this paper analyzing warp drive spacetimes with Warp Factory, which was written by the development team of Warp Factory. And here you can find more information about this toolkit. You can find more mathematics, and there is a lot to it, and again computations. For example, this is energy density for arcubarometric 0 components, and other metrics also shown here, and this is a length metric. Again, this is energy density for length case, and they actually proved that all of these existing metrics violates energy conditions, and they are all non-physical. So it's again, all of this warp physics is just wibbly-wobbly, timey-wimey stuff for now, and so on. And that's it. I hope you enjoyed this tutorial, and see you next time.